So the topic of integration by parts, we have now, over the last however long, been looking at techniques for doing integrals, for evaluating these indefinite integrals, finding the function that is the antiderivative of what you're seeing inside the integral. And sometimes we could just look at that function, like at this first one, an x to the 2/3, okay? To anti-differentiate that, it's very easy to think backwards through your power rule, right? Sometimes we can just look at the function that's in the integral and figure it out, right? Not a lot of technique to that, just using what we know about derivatives, how those work, thinking backwards through that. Sometimes we needed a little bit of help with that, and we picked this idea of a technique called U substitution when we saw that there was multiple functions usually inside of our integral, where if we were to take the derivative of one, it would help maybe get rid of the other, simplifying our integral down into something that we could think backwards through or figure out. And so I would use U substitution for something like this, where the derivative of tangent is secant squared, and I can see that using a U substitution there would help me getting rid of the function and simplifying the integral. But sometimes that's not the case. If we look at this very last one, our functions are like an x and a cosine x, where using that idea of U substitution, subbing in U for x isn't going to help because the derivative of x does not get rid of cosine x. The derivative of cosine x doesn't get rid of plane x. And so U substitution would not be helpful on that last one. And so what we're seeing today is a third option, which is this idea of called integration by parts, of just what else can I do if I've exhausted the other two options and it's not helping me find that integral. I would say I would always try to attack it in the order that is on the board. Always easiest if I can just figure it out. Okay? And then I would go to U substitution, and then if that doesn't work, then I would use this integration by parts idea that we are learning today. Okay? So how does integration by parts work? It is a formula. And what that formula does is it breaks down what is inside the integral into two things. We will let one of the functions inside of our integral be U, similar to what we did with U substitution. We let the other part of what is inside the integral be what we would consider dv, and that would include the dx part of it. And once we've done that, which would be steps 1 and 2, letting one of our functions be dv, the other function in there ends up being dv dx, which we'll look at here in just a second. And then we have to think through a couple other things. When we let one of them equal u, we want to say, okay, well then what is du dx? Eventually then what is du equal to? Because that's what we'll sub in up here. It's du. Okay. And when we figure out what function we're going to allow to be dv, or eventually dv dx, we want to think through, okay, well if that's dv, what was v? What was the antiderivative of that? Because we use that in our formula up above. We take all of those things and we put them into the formula that you see at the top, which is function u times function v minus the integral of v times whatever we got for du here. We clean it up. Hopefully, in the cleanup process, we can think backwards through or use some other technique to evaluate that integral. And then the last thing, don't forget to tack on the plus c, because all of our antiderivatives have a plus c at the end of them as we are evaluating indefinite integrals. Now, as far as formulas go, do I need to know the formula for integration by parts if that's the technique I'm using? Absolutely. That would be something I would have to know to be able to use this formula. They're not going to say, hey, here's the formula for integration by parts, try it out. You got to know the formula for that, which is why we're going to practice a couple here. So today, in leading our way through the notes, all the way through the notes today, I'm going to tell us what we're going to let u equal and what we'll let dv equal. At the end of our notes today, I'm going to talk about, okay, now when you have to make the decision, what would you look for as far as picking which one you would let u be and which one you would let dv be. So given this first example, the integral of x cosine x dx, which is what we saw at the beginning, we talked that it's not one I can think backwards through. It's not one that u substitution is going to be useful for. So I go to this idea of integration by parts. So the two parts that I would break this into would be x would be my first function. I would let u equal x. The other function in there we see is cosine x, and actually it'll be cosine x dx. Thank you. And that's what we're going to let dv equal. So this is u, this is dv, if you were matching that to your formula on the other page. And this first part, I actually a lot of times skip to the second line because we're letting dv equal cosine x dx, which means if I were to divide to get that dv to the other side, dx to the other side, it would look like dv over dx equals cosine x. A lot of times I'll just jump straight to that line right there. dv dx is going to be the other function that we didn't put for you. Once we've identified those, I need two things. I need to take the derivative of u, because we need eventually du equals. So du with respect, try that again, du dx, derivative of u with respect to x. Derivative of x is just 1. Solve that for du, because that's what I need to plug in. I need to sub in something here for du. So if I solve this for du, I would multiply both sides by dx and find out that du actually equals dx, right? 1 times dx is dx. And the other thing I need to think through is what is the antiderivative of cosine of x? What is the function that I had that when I took its derivative, I got cosine x? Just be careful when you're going between those sines and cosines and paying attention to which one is positive and which one's negative, right? What is the antiderivative of cosine x? Sine x, right? Just plain old positive sine x. Okay, so then we follow our formula. U times v minus the integral of v du. So function u was x. Function v, we just figured out, is sine of x, so x times sine of x, minus the integral of v, which is sine x, du, which we showed over here, equals dx. Okay, I'm going to pause there because that's kind of the first time we've taken that information and put it into the formula. So everyone's seeing where everything's going there. Okay. And then the last thing we want to do is clean this up. So I would go to the integral part of it. Do I know this integral? What is the antiderivative of sine x? Negative cosine x, right? Plus c. And then negative, negative. You'll never see me change it from plus c, right? We talked about that last week, is that 2c is the same thing as c because it's representing some constant, and changing its sign is not going to change that either. Would it be wrong if I put a minus c on there? No. It's an equivalent form. We don't know what that constant is representing. Nope, we kind of went through that last week too, because when you end up evaluating a definite integral, you end up, whatever the constant is, it ends up subtracting itself with the second value. So sign wouldn't impact that either way. Nope. Other questions? All right, so that was kind of easing our way into this. Let's look at another example here. Very similar. The second function on this one is an e to the x, so x e to the x dx. Again, today, through our notes, I'm going to kind of help us with what we're going to let u equal and what we're going to let dv equal. Again, on this one, I'm going to let u equal the function x. And then I'm going to let dv be the other part, which means dv dx equals e to the x. This column right here, the u, I want to find its derivative, du dx. Very similar to the last page, is 1, which means du equals dx. Over here, we want to figure out the antiderivative of e to the x. And what is the antiderivative of e to the x? E to the x. Okay. And then again, putting those into our formula. So our integral is going to equal function u, which is x, times function v, which is e to the x, minus the integral of v, which is e to the x again, times du, which we said equals dx. And then clean it up. Okay, well, the integral of e to the x is e to the x plus c. I would leave it like that, but again, if you ever see, as you kind of scan through their common factors, sometimes they'll factor those out like they all have an e to the x. So always looking for those equivalent forms. You might see something like that as a multiple choice option. Keep that in mind, is comparing yours to a multiple choice option might be just the difference of a GCF. Okay, and those show up a lot with like our e to the x's and such. Okay. All right, let's get a step more complex here. The integral of x squared e to the x dx, which looks very similar to the one we just did, right? The reason this one gets more complex is our u function. So again, I would let u equal x squared and dv equal e to the x dx, which means dv dx equals e to the x. We already did that on the last page, right? That means v equals e to the x. Finally, though, when I take the derivative of u, we don't get 1. We get 2x, solving for du. I get 2x dx. So what happens when I go to put that into my formula? Let's see, u is x squared, v is e to the x, minus our integral. And if I just kind of show it this way, and then I'm going to clean it up for just a second, v is still e to the x, times du, which is 2x dx. A couple of the things I would do in that integral is anytime I have multiplication by a constant, I get that out of there so I don't have to factor that into my integral part of it. So I'm going to slide that 2 out front of the integral. Okay, but that's still leaving me with e to the x times e to the x dx, right? So as I'm supposed to clean this up and get an answer, I'm trying to evaluate the integral x e to the x dx. And I can't think backwards through that one. In fact, we've already talked about that, right? Because isn't that the exact same problem? This right here? Isn't that what we just saw on this page that we required integration by parts to solve? Okay, so what I'm showing you is the most complex ones might require you to do integration by parts twice. Now, we already did the work for this one, so I'm not going to force us to do the work again on this one. We're just going to kind of steal the work we just did on the last page, but then we'll look at one where we actually do kind of show that work side by side here. But this, we would have to do integration by parts again. So we get x squared e to the x minus 2. And then if I go steal our answer from the last one, it's going to be this guy, x e to the x minus e to the x plus c. And finally, distribute the negative 2 through. And again, as always, I'm not going to put a coefficient on c, so it's negative 2 times c is still some other constant, right? And I would leave my answer like that unless I was trying to match it to some multiple choice option in which I would look to maybe take out a GCF of e to the x, but there are no like terms we can combine other than that. Okay, any questions on that? So basically we combined the last problem and this problem together in one because we would have had to do our integration by parts again here like we did on the last page. So let's actually try something like that. Okay, integral of 3 sine squared, or sorry, integral of 3x squared sine x dx. Again, until we get to our last page here, I'm going to tell you what to use as u and what to use as dv. So again, on u, I would use the 3x squared. And dv would be sine x dx, or dv dx would be sine x. So we need two things over here, our derivative of u, which would be 6x, or du equals 6x dx. We need our antiderivative of dv. So antiderivative of sine x, careful, negative cosine x, right? Because the derivative of cosine of x would be negative sine of x, but since it's a positive, we need a negative cosine of x. Okay, so putting those into my formula, we get 3x squared times negative, so I'm going to put that negative out front, cosine x, minus the integral of negative cosine x times 6x dx, which we can clean that up a little bit. I'm going to bring the negative out front as well, so a negative negative becomes plus. Bring the 6 out front, and then we're looking at the integral of x cosine x dx. And then this part again, which we've kind of seen already, we would do integration by parts a second time as we think through our options. I can't think backwards through the antiderivative of x cosine x. U substitution does not help on that one. So we would go back to our idea of integration by parts. So I'm going to let u equal x. I'm going to let dv dx equal cosine x. Take our derivative of u. Du equals dx. Our antiderivative over here would be sine x. And fill in my formula here. So u is x times v is sine x minus the integral of v, which is sine x, times du, which is dx. So kind of focusing on that part again. Antiderivative of sine x. Antiderivative of sine x. Negative cosine x, right? With the negative that's already out there is going to be positive cosine x plus c. And we still got all this sitting out front. And send that 6 through. We get that ugliness. Okay, so through all of our notes today, I told you guys what to let u equal and what to let dv equal. And what it kind of looked like is one of two things. It was the x, or it was the first thing, right? Which kind of happened for all of our examples today. There is actually an order to attacking it. So if you plan to be successful with this integration by parts, a little mnemonic device to help you remember, which I don't know how you're going to remember that, but find some way, is LIPIT. Natural log or your logarithmic equation, logarithmic expression would be what I would pick first if that was ever in my integral. And then if there was an inverse trig function, I would pick that second. And then polynomial. Well, this is where we picked up today. We did not at any point in all of our notes see a natural log. We never saw an inverse trig function. We did see polynomials. Polynomials, x, x squared, 3x squared, all of those are polynomials, right? So that's what I would pick for my u, if that's an option. And then exponential, and then the last thing I would pick is a trig function in that order. If you think about, if I were to not pick a natural log as my u, I have to think backwards through its antiderivative, right? So if dv equaled the natural log of x, what function's derivative is the natural log of x? We don't want that to happen because I don't know what function's derivative is the natural log of x. So that's why I'll let it be my u. Now, as with everything, this is kind of a trial and error thing. So sometimes maybe there's two options that are equally as good to pick, and you got to figure out which one is going to be probably your more beneficial way to pick. And just like I said with u substitution, sometimes you just have to pick one. Pick one and try it out. And maybe you pick the right one and we are on the right path, and maybe you realize you're on the wrong path and you start over, okay? But the other thing I'm going to tell you guys is, again, with everything, we got to try them. So if you guys walk in tomorrow and you have this written here and no work, okay, yeah, a little suspect, right? So make sure that we are showing me that work on our assignments as well, because you're not getting this answer by looking at that integral and jumping to this, right? It's going to take a little bit of work. Give yourself plenty of space to work through these. You don't have a ton. You're on page 350. You're doing 1 and 2, and then 3 through 13 odd.